Okay, our first of two examples of VOP, variation of parameters, to solve a second order differential equation is going to be solving this equation. Y double prime plus y is equal to cosine x. So the first thing we're going to do, as usual, is get the homogeneous solution. And we take the characteristic equation. So m squared plus 1 is equal to 0. And if you remember what that is, m squared has to be a negative 1. So that's going to be m equal to plus or minus I. Again, you could plug that into the quadratic formula and you'll get the same result. So if we had alpha plus beta I, the alpha is a 0 and the beta is a 1. So we're going to have a cosine x and a sine x. So this tells us that, and I'm going to write this way over here. The homogeneous solution is going to be a constant times cx, cosine of x, plus a constant times sine of x. So c1 cos x plus c2 sine x. And one more time, let's talk about where that came from. It's cosine x, it's cosine 1x, because beta is a 1. Alpha is a 0, so we really have the whole thing being multiplied by an e to the 0x. But e to the 0 is just 1, so we left that off. So there's our homogeneous solution. This would be our, we could call this our y1 of x, and this our y2 of x. And why don't we go ahead and, since we've got the homogeneous solution, let's just compute the Wronskian right now. We know we need that to find the particular solution, and we've got y1 and y2 here, so the Wronskian is the determinant of the matrix, where you take y1 and y2 and put them right here on the first row. So let's see. I can leave the constants off in the Wronskian. I'm going to put just cosine x and sine x. So I'm going to call this is y1, that's y2. All right, we can leave the constants off. So we take cos x, sine x, and then below that we take the derivative of both of those functions. First derivative. Derivative of cosine is negative sine. Derivative of sine is cosine x. So that's the Wronskian, and we can simplify that now. We know the determinant of a 2 by 2 you get by multiplying this diagonal minus multiplying this diagonal. So we would get cos x squared minus a negative sine x squared, so that's plus sine x squared. And the Wronskian is equal to 1. Couldn't be much more easier. Could not be much more easy than that. Okay, so in our formula, which I wrote up here as a little cheat note, the denominators here, the Wronskians, are just going to be 1 in both cases. All right, so the particular solution is equal to negative y1, which is negative cosine x, times the integral of sine x cosine x. I'm going to go ahead and put over 1 just as a reminder that that's our Wronskian, dx, plus sine x times the integral of cosine x times cosine squared x over 1 dx. So I think I'm going to leave some of the calculus 1 for you to do. In this integral, we could say let u equals sine x, doing a u substitution, then we got du being cos x dx. So that'll get you going on this integral. And what do we do on this one? Cosine squared is a tough one to integrate unless you use an identity which, I'll say use cos squared x being equal to 1 plus cosine of 2x. And then when you do that, you're going to need, when you take the derivative of cosine 2x, you're going to end up with a sine 2x. So where you're also going to need sine 2x as an identity is equal to sine x cosine x. So you'll need both of those identities. Doing some calculus, we end up getting 1/2 x sine x as our particular solution. So between our homogeneous and our particular, we get y equals c1 cos x plus c2 sine x plus the particular, which was 1/2 x sine x. And in the general case, basically you're going to get something that looks like the homogeneous solution in the particular solution. I wouldn't have been surprised if we had plus something cosine x. In general, it's going to be something like some function of x times sine x, because the homogeneous solution has sine x in it. And because it has cosine x in it, it would be plus cosine x times some other function of x, which in this case was a 0, because there was no cosine x in the particular solution. Okay, we have one more example we'll do in the next video.